Hello! In this video, we are going to prove the following theorem. Let a be a real number greater than 1. Then for all positive integers n, a to the power of n is greater than 1. So let's first remind ourselves of our definition of non-negative integer exponents. Let a be any real number. Then for each non-negative integer n, we define a to the power of n to be a real number, recursively as follows. A to the power of 0 is going to be equal to 1, and a to the power of n plus 1 will be equal to a to the power of n times a for every non-negative integer n. Now notice, according to our definition, we can show for every real number a to the power of 1 is equal to a, because we can take a to the power of 1, re-express 1 as 0 plus 1, but then according to the recursive part of our definition, a to the power of 0 plus 1 is a to the power of 0 times a. And according to our definition, any real number to the power of 0 is 1, so this is just 1 times a, and then 1 times a is equal to a. So we see, given any real number a to the power of 1 is equal to a. So now, let's get into proving this theorem. Now, we're going to prove this statement by induction. So let's start with the base case. In the base case, we're trying to prove that this is true in the case where n is equal to 1. So we want to show that a to the power of 1 is greater than 1. Now we know any real number to the power of 1 is itself. So a to the power of 1 is a. And since a is greater than 1, we can substitute a for a to the power of 1. We have a to the power of 1 is greater than 1. And that's it. We have shown that this is true in the case where n is equal to 1. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary positive integer n, and we assume a to the power of n is greater than 1. The whole goal of the induction step is to show that a to the power of n plus 1 is greater than 1. Now, according to the recursive part of our definition of exponentiation, a to the power of n plus 1 is equal to a to the power of n times a. Since a is positive, if we multiply a on both sides of this inequality, the sign of the inequality remains the same. We get a to the power of n times a is greater than 1 times a. And 1 times a is equal to a, so substituting a to the power of n times a for a to the power of n plus 1, we have a to the power of n plus 1 is greater than a. Now since a to the power of n plus 1 is greater than a, and a is greater than 1, it follows that a to the power of n plus 1 is greater than 1. And that's it. That was the whole goal of the induction step. So this completes the induction step. Because we've completed both the base case and the induction step, this closes the induction. So by mathematical induction, we have proven for all positive integers n, a to the power of n is greater than 1. And so this completes the proof. And so yeah, that's pretty much it for this video.